Okay, on the last video, we talked about the multiplication principle and permutations. Recall with permutations, order is important. You're counting the number of ways of arranging a certain number of objects, okay? So quick review on that. How many permutations of the three letters chosen from A, B, C, D, and E? That could be, now we have a formula for that. It's a permutation. Usually read it as 3 chosen from 5. The formula is 5 factorial over 5 minus 3 factorial. There would be 60 permutations, ways of arranging any 3 letters chosen from those 5 letters. Now, if you started to list all of those 60, think about what your list would look like here. You would have, for example, I could choose ABC as my 3 letters, and then all of the permutations of ABC, ACB, BAC, BCA, CAB, CBA, there would be 6 permutations of those 3 letters. And we know that, right? Because we know the number of arrangements of 3 objects would be 3 factorial. So there would be 6 arrangements. Okay, well, you could have chosen A, B, and D as your 3 letters. And again, there would be 3 factorial or 6 ways of arranging those. ABE could have been your 3 letters, and so forth. So these red circles are the 3 different letters that you chose, and then in each of those columns there would be 3 factorial or 6 arrangements of just those 3 letters. Okay, so there's 10 of these, so 10 times 6, there's your 60 permutations. Now combinations, we don't care about the order of those letters. We're just asking, what are the combinations? What are the possibilities of 3 different letters that you could select from A, B, C, D, and E? We don't care about arranging them, just what 3 letters do you choose? So the number of combinations of those 3 letters chosen from A, B, C, D, E would just be these top entries in the column, right? Or any one of those, but okay, so there would be 10 of those. So there's fewer combinations than permutations because we don't care about arranging them, okay? So the number of combinations, what we were just talking about here, is just those 3 letters, any possibility of 3 different letters, I've got them here. And so essentially what you're doing is you're counting the number of permutations, but then you're just dividing that by 3 factorial, the number of arrangements for each combination of 3 letters that you choose, okay? That makes sense. We had 60 permutations. If you divide that by 6, which is 3 factorial, that gives you the 10 combinations. Okay, so if we combine that, it really is just the number of permutations divided by k factorial, but we can put this all into one formula. The number of combinations of k objects chosen from n objects. Okay, different notations. You can do the same, similar how we did with permutations, capital C, n comma k. Or what's very common with combinations is almost looks like a matrix or a vector that we've been talking about earlier, but it's n choose k is how we usually read that. Okay, you should recognize n factorial over n minus k factorial is the number of permutations, and we're just going to divide it by k factorial, so we just have an extra k factorial on the bottom. Okay, so let's see some examples of combinations. So some problems you'll see, you have to kind of read into them to decide whether it's a combination or a permutation. You have to decide if order matters or not. So one kind of key common code word, if someone asks for how many ways to form a committee of 3 people, a committee of 3 people doesn't really imply any kind of an order, right? We're just selecting 3 people, in this case from a group of 7. Now, you can make a committee question where order does matter. For example, what if I was forming a committee where I was going to assign a president, vice president, and a treasurer? well, then not only am I selecting 3 people, but I'm assigning them roles, which implies an order, right? But in this case, if it's just asking for the number of committees, that is straight up just a combination. So this would be of 7 people, I want to pick any combination of 3 people to serve on the committee. It's fine usually to leave it like this, but just to give you a number, show you how you work it out, that would be 7 factorial over 3 factorial times 7 minus 3 factorial. And canceling out without a calculator, if it's not too big of a number, sometimes it's not too hard to do this. If you expand 7 factorial, 7 times 6 times 5 times 4, 3, 2, 1, I could just stop at 4 factorial, knowing that I could divide 4 factorial by the 4 factorial that's in the denominator. And of course, 3 factorial is 6, so that would cancel out with the 6, and you're just left with basically 7 times 5, there's 35. All right. Now this next question is a good preview of what you're going to see more of. You know, we have these formulas now for the multiplication principle, permutations, combinations, but oftentimes your questions are not as simple as this first one, where it was just straight up the definition of a combination. So what if, this is part B, we're choosing 3 people from a group of 7 to form this committee, but what if we know that there's 2 people in this group of 7 that cannot serve on the same committee? Maybe they just don't get along, something, who knows, right? Now, how many possible committees could we form? Okay, we can't just do this with a formula. So sometimes you have to modify and manually count how many committees would contain those 2 people that can't serve on the same committee together. And we're going to subtract them out from the 35 possible committees. So the way I did it is I thought about, let's call those 2 people that can't serve together A and B. So our 7 people are A, B, and then there's 5 other people, right? That makes a total of 7. So if you think of the number of committees that have 3 people that have A and B on it, you could have A, B, and 1, A, B, and 2, A, B, 3, A, B, 4, A, B, 5. There's 5 committees that could possibly have those 2 people on it. So what we would do with that 5 is subtract it from the 35 possible committees, and we have an answer of 30. Yeah, let's try this one next, since we're on the subject of committees. How many ways can you form 3 committees of 5 people from a group of 15 if people are allowed to serve on multiple committees? So even though we have 3 committees, there could be a person who serves on all 3 committees, or maybe just 2 of them, or 1 of them, right? So now I'm thinking of really the multiplication principle, because I have 3 committees, so I need to count the number of possibilities for each committee. So there's the multiplication principle, committee 1, committee 2, committee 3. But each one of those, how many ways can I form committee 1? Well, I can choose any 5 of the 15 people. For committee 2, same thing. If whoever's on here, I still have 15 people to choose from. Even if those 15 people were on committee 1, they can still serve on committee 2. So it's 15 choose 5 for committee 2 and 15 choose 5 for committee 3. And the answer, I would multiply those together, right? So it's combining, if you will, the multiplication principle with combinations. Well, what if nobody is allowed to serve on more than 1 committee? Okay, that would seem to make sense in certain situations. So how would I count that? I'm still going to start with the multiplication principle. Committee 1, I can choose any 5 of the 15 people. For committee 2, though, whatever 5 people end up on this committee, I no longer can select from them. So I would only have 10 people now to choose from for committee 2. And if you think about it, Once you choose 5 people for committee 1 and 5 people for committee 2, there's only 5 people left in our group, and they're automatically going to become committee 3. But if you stick with combinations, then it would be 5 choose 5. How many ways are there to choose 5 people from 5 people? There's one way. This, by the way, can give some insight, I promised earlier, of why 0 factorial, we need to define that to be 1. Because if you use the formula for this, you would get 5 factorial over 5 minus 5 factorial, which is 5 factorial over 5 factorial, 0 factorial, right? And we know the answer is 1. There's only one way to form a committee of 5 people from 5 people. So do you see, that's why we have to have 0 factorial defined to be 1. Otherwise, it's going to cause problems, right? It's going to give us the wrong answer. So, okay, let's move on to another scenario for combinations where order is not going to be important. Let's say you have a jar. This is a common scenario that you'll see. Say you have a jar that has 5 green, 4 red, and 3 black marbles. So we have a total of 12 marbles. You randomly choose 3 marbles, and we're going to count the number of ways of getting, for example, all green or all black. So order is not important, right? If you get a red, green, and a black marble, the order you pick them doesn't really matter. You still have a red and a green and a black marble. So these are going to be combinations. The number of ways of getting all green, well, there were 5 green in there, and we can get any 3 of the 5 green, any combination of 3 of the 5 green. So it would be 5 choose 3. All black marbles, well, there are only 3 black marbles in there. So that would just be 3 choose 3, which of course is just 1. What about 1 of each color? A green, a red, and a black one. Well, let's think the multiplication principle. I want any one of the 5 green marbles. That's 5 choose 1, which does come out to be 5. It makes sense. How many ways can you choose 1 marble from 5? 5 ways. But if you stick with the combination format, it's going to help you in the long run. So even though it is just 5 times 4 times 3, you can still think of it in terms of combinations. Again, that gives you an answer of 60. 2 green and 1 red. Well, first I'm going to count the number of ways of getting any 2 of the 5 green marbles. And then I'm going to multiply that by 4 red marbles, and I want to pick 1 red marble. No green marbles. Okay, well, how many of them are not green? If you go back and count them, there were 7 that were either red or black. And so we would want to pick any 3 of the 7 red or black ones. Those would be not green. Okay. What about how many ways can we pick at least 1 green? And you're going to see a lot of this going forward, counting the number of ways or even doing probabilities where they asked for at least 1 of something. Because what's incorporated in picking at least 1 green marble? Well, you could pick 1 green marble and 2 not green, or you could pick 2 green and 1 not green, or all 3 of your marbles are green. All of those entail picking at least 1 green. So in the world of adding and even in probability, if it's going to happen, if you want to count the number of ways of this happening or this happening or this happening, we're going to count those ways and add them together. So or kind of means adding. Okay, and these are just combinations, right? 5 choose 1. Remember the non-green ones, there's 7 that are not green, so this would be 7 choose 2. 2 green, 1 not green, all green. If you want to be consistent, right, you're picking 0 green from the 7 that are not green, which actually comes out to be 1 as well if you use the formula. You don't have to put that in there, right, because we've already picked all 3 green marbles, but you know, kind of shows that you can be consistent as well. Now I do want to show you there is another way to count this. at least green, and this is a preview for a big idea in probability, is to think about the complement. Here's what the complement is. If you pick 3 marbles, in terms of the number of green marbles, you're either going to get no green marbles or you're going to get at least 1 green marble, if you think about it, right? That's it. So the total number of possibilities of picking 3 marbles from all of our marbles, which is 12, and that would be 12 choose 3. We already counted the number of ways of picking no green, which was 7 choose 3. And the only other thing that could happen is you get at least 1 green, which I'll call X temporarily, which is what we're asking for right here. So what you could do to solve for this is just subtract those, right? Subtract 12 choose 3 minus 7 choose 3. And if you work that out on a calculator, you'll see that those numbers are identical. Okay, I got one more example here. Oh yeah, back to committees. Back to committees here. Let's say UC Davis holds a conference on student fees in which 20 undergrads, 20 grad students, 20 transfer students, 20 international students, and 20 faculty are invited. How many committees of 10 undergrads are possible? Okay, again, committee is a nice code word. If there's no assigning roles for anybody on the committee, then order is not important. So that would simply be, there's 20 undergrads, we want to pick any combination of 10 people. So 20 choose 10. Comes out to be a pretty big number, 184,756. How many committees of the same type are possible? Meaning, of 10 people, if we're going to form committees of 10 people, how many ways are there to get all undergrads, all 10 are graduate students, all 10 are transfer students, and so forth? Well, makes sense. There's the equal amounts of each one, right? So we just counted the number of ways of picking all undergrads was 20 choose 10. It would be the same for all graduate students, transfer students, international, and faculty. And we want to count the number of ways of that happening or that happening or that happening. We're just going to add these together. Or since they're all the same, just multiply it by 5. Okay, now here we go. How many committees of 10 contain at least 2 people from different groups? Okay, so maybe you have 8 graduate students and 2 transfer students, or 2 undergrads, 2 grads, 2 transfers, 2 internationals, and 2 faculty, right, in your committee of 10 people, which would seem to be the most logical thing to do. But anyhow, right, that's a lot. We're trying to count the number of ways we can get a committee of 10 where we get at least 2 people from different groups, okay? So I think the best way, okay, going back to we talked about this earlier, anytime somebody asks you how many ways for at least 2 people or at least something to happen, consider the complement, consider the opposite. What's the only other thing that can happen if you, other than picking a committee of 10 people where at least 2 people are from different groups, everybody's from the same group, right? And we just counted that up here. So think of it this way. The total number of 10-person groups is the total number of ways. They're either all going to be from the same group or at least 2 people are going to be from different groups. So we can kind of work that backwards like we did earlier. The total number of 10-person groups is, out of all 100 people, number of ways of selecting 10 people. We counted this up here, the number of ways that they're all from the same group, and this is what we're looking for, so you could just subtract those 2.